looking at page 355, section 4.8. Page 355, section 4.8. Looking at applications and models of these trig functions we've been working on. Now, to begin with example number 1, they asked me to solve a right triangle. When they ask me to solve a triangle, in this case it's a right triangle, but it won't always be. In subsequent sections, they'll give us other things. But if they ask me to solve a triangle, they literally mean find all of the missing pieces. So, like you'll notice in our example, they gave us one of the sides and one of the angles. So they gave us angle A and they gave us side B, and they say solve the triangle. That means find every other missing piece. Find angle B, find angle C, find little a, and find little c. All right, a couple things that are really important. They won't always draw the triangle for us. Sometimes they'll write it out like they've done here, kind of written out in just a sentence or a paragraph form, and I'll have to go back and draw the triangle. When I draw it, I'm going to use lowercase letters for the sides and uppercase letters for the angles. And the angles and the sides with the same letter have to be opposite of each other. The angles and the sides with the same letter have to be opposite of each other. So, like, what we mean by that is if I've got capital angle A over here, straight across from it is lowercase side A. Capital angle C, straight across from that, lowercase side C. Capital angle B, straight across from that, lowercase side B. If you don't draw it that way, you won't get the right answers when you're asked to draw it yourself. So it's critical that we have the angles and the sides with the same letter opposite of each other. Okay, so we go through and start solving. They actually told us what angle C was, right? What's this little symbol down here tell me?
90 degrees.
90 degrees, right. So angle C is a right angle. Then how do I find angle B? Yeah, subtract from 180. So I could do 180 minus the 90 degree angle and then minus the 34.2. Or somebody said add the two of them together and subtract from 180. That's great too. So we'll end up with 55.8 for angle B. All right, now I need to go find my side. So let's start with side A. If I'm going to find side A, I'm always going to go back and use the given information. You don't have to, but if I did something stupid in my subtraction right here and I made a careless mistake, if I use angle B to then find side A is going to be wrong as well, right? So if I can, I'm only going to go back and use the given information. So if I'm trying to find little a, and I know big A and I know little b, because that was all that was given. Okay, I know this angle. I'm looking for what's opposite of it, and I know what's adjacent to it. What deals with opposite and adjacent? Tangent, right. So I'm going to want to use tangent then. And so I'll say the tangent of angle A is equal to opposite, little a, over adjacent, 19.4. All right, how are we going to get little a by itself? Perfect. Multiply both sides by 19.4. Do you want to be in degree mode or radian mode? Degree mode. So we can type it in and we've got our answer. All right, how can I find C? I could use Pythagorean theorem. Yeah, that's not nothing wrong with that. My only thing is I make careless mistakes so easily that if my A is wrong, if I do A squared plus B squared equals C squared, that means my C is going to be wrong as well, right? So we are going to come back to the Pythagorean theorem idea in just a second because that's a great idea. Is there a way that I could find C using only the given information? If I'm trying to find little c, can I find that if I know angle A and little b? What would I use? Cosine, right, because I've got adjacent and I'm looking for hypotenuse. So I'm going to say the cosine of my angle is equal to the adjacent side, 19.4, over the hypotenuse c, which is what I'm trying to find. All right, c's in the denominator this time, so how do I find c? Yeah, both of you are right. You can multiply by c or you could cross multiply. Whichever way you think of it, you're going to come up with the same thing. Because if you cross multiply, cosine 34.2 times c is equal to 19.4 times 1. Or if you multiply both sides by c, you're going to get the same thing. All right, so once I'm here, how do I get c by itself? Divide both sides by cosine. Perfect. And again, throwing that into my calculator in degree mode. All right, so now let's go back to that idea of Pythagorean theorem. If I didn't use the Pythagorean theorem to find my sides, then I get to use the Pythagorean theorem to check all of my sides at one time. So it gives me a really fast, easy way to know that all my work is correct, because I can go back and do a squared plus b squared equals c squared and see if they're the same thing. Now, I'm rounding these sides to like 2 decimal places, so they're not going to be perfect. If I were keeping 8 decimal point accuracy, then yes, they would be exactly equal to each other. The fact that they're off by like 3/10 here, no problem at all with that. So I don't have to do that, but if I want just a quick, easy way to check my work and know that I've got my sides correct, since I didn't use Pythagorean to solve, I can use Pythagorean to check. All right, bottom of 355, they remind us of a couple of bold print terms that we've seen before, angle of elevation and angle of depression. They tell me the term angle of elevation denotes the angle from the horizontal upward to an object, and the term angle of depression denotes the angle from the horizontal downward to an object. So we've said before, it's kind of like if you looked up to see the top of a building, then that would be an angle of elevation. Or if you look down into the subway, that would be like an angle of depression kind of thing. So example number 2 over on page 356. Example 2 says a safety regulation states that the maximum angle of elevation for a rescue ladder is 72 degrees. If a fire department's longest ladder is 110 feet, then what's the maximum safe rescue height? Okay, here is my sad attempt at a fire truck right here. So we've got our fire truck whose angle whose ladder is 110 feet long, and the highest degree of elevation that keeps that thing safe and the truck balanced and all that good stuff is 72 degrees. That's as high as it can go. So how far up the building is that going to stretch? All right. Well, I know this angle. What's 110? Adjacent, opposite, hypotenuse? Hypotenuse, right, because it's directly opposite the right angle. So I know this angle, I know the hypotenuse, and over here I'm looking for what? Opposite or adjacent? Opposite. So what do I want to use? Sine. Good. So I'm going to say the sine of my angle is equal to opposite over hypotenuse. How am I going to get x by itself? Multiply by 110. So the ladder will reach 104.62 feet up the side of the building. So if you're 104 feet up the side of the building, we got you with the ladder. If you're 110 feet up, we're getting out the trampoline for you. Jump, lady. Jump, lady.
It says 104.62.
Yes. All right, look at example 3. They were kind enough to give me a figure with example 3, or I might have not understood what they were saying. Example 3 says, at a point 200 feet from the base of a building, the angle of elevation to the bottom of a smokestack is 35 degrees, and the angle of elevation to the top is 53 degrees, as shown in the figure. Find the height S of the smokestack alone. So here's the drawing that they gave us in the textbook. And I thought it might be easier to kind of break that apart into 2 separate color-coded triangles so we could see it a little better. So here's the first one that says I'm 200 feet away from the base of the building, and if I have an angle of elevation of 35 degrees, I can see to the top of the building. So they had the building labeled A, so the top of the building, this length, this height over here, would be A. The second thing that they said is that if you wanted to see not just to the top of the building, but to the top of the smokestack, then it would take a 53 degree angle of elevation. So that's our second triangle over here. We're still 200 feet away. Angle of elevation is 53 degrees, but that's to see not only to the top of the building, but then also on up to the top of the smokestack. So this height over here would be the smokestack plus the building. It would be S plus A. I'm trying to find just the smokestack, but I'm not going to be able to solve for S until I know what A is. So let's start over here and let's solve for A, and then we'll be able to plug that in. Okay, so what am I going to use to solve for A over here? Sine, cosine, or tangent? Tangent, right. Because I am looking for the opposite A, and I know the adjacent 200. All right, how do I solve for A? Multiply by 200. In degree mode in my calculator, and I find out that the height of the building is 140.04. All right, so now I can come back over to this problem. Since I know A, the only unknown would be S, and I'd be able to solve for that. So I'm going to set this up again, exact same way we did a second ago. I'm going to use tangent of the angle is equal to opposite, which is S plus A, over adjacent, which is 200. So S plus A over 200, and I can go ahead and put what we just found for A, 140.04. So tangent was opposite over adjacent. S plus A over 200. We already found A was 140.04, so let's go ahead and put that in. All right, now we're trying to get S by itself, right? So what do you want to do first? Okay, multiply by 200, and then subtract 140.04. Now, anytime you can, it's a good idea to just put this whole string in your calculator at one time. Because if you put tangent of 53 in and you round that to 2 decimal places, and then you multiply that by 200 and you round that again, and then you subtract the 140.04 and then you round that again, you have the likelihood of your answer being off by a tenth or two at the end by the time you round multiple times. So it's a good idea if you can just to put the tangent of 53 in, leave all 8 decimal places there, multiply that by 200, leave all 8 decimal places there, subtract the 140.04, and then round just that final answer. So that would be the height of our smokestack. All right, you may not care a whole lot about heights of smokestacks, but you might care a little more about the swimming pool in your backyard. So example number 4 says a swimming pool is 20 meters long and 12 meters wide. The bottom of the pool has a constant slant so that the water depth is 1.3 meters at the shallow end and 4 meters at the deep end as shown in the figure. Find the angle of depression of the bottom of the pool. Okay, so here's the deal. You're designing a pool for your backyard. You're going to stick with just a basic rectangular shape, but you want to be able to set the depth of your shallow end and your deep end to what you want. So maybe you want a 3-foot shallow end and you want a 7-foot deep end. You're going to then need to figure out, okay, how do I slant the bottom of this so that I get the depth that I want on this end? That's exactly what we're looking at here. So it says the swimming pool is 20 meters long, so we can go through and give that dimension, 20 meters long and 12 meters wide. The bottom of the pool has a constant slant so that the shallow end is 1.3 meters and the deep end is 4 meters. Now, if this deep end is 4 meters down here, then I could go through and say if I take 4 and I subtract off the 1.3 for the shallow end, that gives me an extra 2.7 meters for the deep end. Okay? So they gave me the total of 4 over here. We needed to break that down into 1.3 and 2.7. And we want to know what's this angle of depression right here. So since I'm really just concerned with this triangle right here, I'm going to redraw the figure so that I can focus just on that triangle that has the length of 20, the depth of 2.7, and trying to find that angle. By the way, if you're reading that word problem, it says a swimming pool is 20 meters long and 12 meters wide. Where did the 12 meters wide go? Nowhere. It's a distractor. A distractor is an additional piece of information given in a word problem that you don't really need because they want to see, do you actually know what you're doing, or are you just like throwing in every number that they give you somewhere in the problem and hoping to come up with the right answer? So you won't always use every piece of information in your problem. Don't let that concern you if you have a piece that you don't need. Thanks so much. Trig word problems aren't hard enough without you intentionally trying to trick me with distractors. Thanks so much. Appreciate that. Okay, so let's solve our triangle. We've got this guy right here that we're trying to find, our angle. We know what is opposite of it, and we know what is adjacent to it. So let's use tangent, and we can say tangent is equal to opposite over adjacent. Now, this is the first time today we've seen one of these. What do we do when they give us the answer and we're looking for the question? Inverse, right. That's our Jeopardy button, right? Inverse trig, second tangent, or inverse tangent. So we can type that in, and it tells me I need that angle of depression to be 7.7 degrees.
That's the same thing as arctan, right?
Yes, arctan, inverse tan, same thing. All right, last thing I want to mention to you, on the top of page 357 is the idea of bearing. If you have never been a Boy Scout or you've not done, like navigation or that type of thing, you may not be familiar with bearing, and some of our word problems, they deal with it. So let's talk about it for just a second. It says, in surveying and navigation, directions are generally given in terms of bearings. A bearing measures the acute angle a path or line of sight makes with a fixed north-south line. So when you're given a measurement in bearing, you're going to have a letter, either N or S for north or south, and then you're going to have a number, which will be your angle, and then you're going to have another letter. It'll either be E or W for east or west. So here's the idea. Remember it said that it measures the acute angle a path or line of sight makes with a fixed north-south line. Okay, so if you're looking at a compass, you've got your north, your true north there. So if we look at that as a north-south line, you could have your angle coming off of the top part of that line, off of the north part, or coming off of the bottom part of that line, off the south part. That's what determines what your first letter is. So you'll notice that in this first figure, we use the bottom half of this line, the south part of this line, to draw off of, so that's why we start with south. Our angle was 35 degrees, and we went to the east. We didn't come over here to the west of that line. We went to the east of south, and so that's why our last letter here is E. So we would say that's 35 degrees east of south. All right, for the second one over here, are we drawing off of the north or off of the south? North, so we're going to start with N, and then we'd put our number 80. Did we go to the east or the west? To the west, right. So that would just be N80W, which is 80 degrees west of north. Okay. Now, they gave us some really great applications here in the textbook. They go on and they talk about a physics application, which is harmonic motion, and you can play around with that. That'll be your challenge tonight, is simple harmonic motion. That's what your challenge problem deals with. But there are lots of other real-world applications to these trig functions that we do use all the time. We saw last week one of the problems that we did. It was a challenge problem. It was number 83, and we worked through it together in class. It dealt with the, I think it was the rainfall amounts in Seattle, Washington over the course of a year, right? We plotted those points, and we found out that it looked like a trig curve. It actually looked kind of like a cosine curve. And we knew that it wasn't parabolic because it wasn't going to keep going to infinity. When you're in Seattle, you may feel like there's an infinite amount of rainfall every year, but there's really not. It is going to cycle back down and back up again and down and up. So we saw that rainfall amounts typically follow a cycle, a period, and we saw that it looked trigonometric. Some other things that do that are like the tides. If you think about, you go high tide, low tide, high tide, low tide, it's going to go up, down, up, down, up, down, and it would look very much like a trig curve. Temperatures. We've seen this week that temperatures don't always do what they're supposed to do, but they do track the temperatures over the years and say, okay, this is what the typical high is for this time of year and what the typical low is. And if you think about Savannah, it definitely during the winter is in the low temperatures, and then during the summer is in the high temperatures, and there's a big difference between those two. So we would have a big change, in that up and down cycle type thing. Another thing would be hours of sunlight. We talked about how they can, in farmers' almanacs, tell us what the tides are going to be, and what the sunrise and sunset are going to be, and what the cycles of the moon are going to be for 5 years from now. That's because they're periodic, they're cyclic, they follow a trig curve. So that's another application of this. But something else that I think is a really fun, quirky application of trig functions that you may have never heard of before is money and banknotes. If you've got like a $1 bill or $5 bill or anything like that in your wallet, go ahead and grab it for a second. This is not my idea. This is something that came from a television show called Numbers that was on several years ago. In one of their first shows, they were dealing with some counterfeiters, and they use something called Gila Shay. All right, Gila Shay is very intricate designs produced by using a combination of graphs of variations of the sine curve. So here's an example. Let me jump over to this website for a second. Here's an example of some Gila Shay patterns, and this second one here is very much like what you would see on currency. So if you're looking at that, you see how it kind of looks like, I mean, you can easily see in here, here's the sine curve, right? And then maybe we've just done a little bit of a shift and done the same thing, or we've done a little bit of a shift this way and have the same thing running in between, or maybe we've shrunk it or we've stretched it and then we've come up and done another one of the same thing. So it almost makes like a three-dimensional looking kind of pattern. All that is hundreds of sine curves, slightly varied and set together. So if you go back to your dollar bill, you can see what kind of looks like on here, almost like cobweb in here. You can really see it down here. That's Gila Shay. And the purpose of that intricate design is to prevent counterfeiting on currency, bills, anything like that. It just makes it harder for somebody to reproduce if it doesn't have those patterns on there. Another really random place that you find the sine curve, have you ever heard of Fabergé eggs? They're these really expensive eggs because of intricate designs on them. So in any case, I thought that might be kind of fun for you to see some of the random places where we would use the trig curve that we might not expect to see sine or cosine. Okay, so here's our homework for tonight.
That's what that thing is? Yeah.